Welcome to Lecture 10A of Differential Equations and Linear Algebra. In Lecture 9A, we looked at a lot of examples of what are called phase lines for autonomous ordinary differential equations. We thought about something called linearization near equilibrium points to help us understand the phase line. And at the end, we did our first example of a bifurcation problem. Lecture 10A does all that stuff again in a lot more depth and with more examples of bifurcations. We'll also, with this linearization, write it down as a theorem, a linearization theorem, sometimes called the Hartman-Grobman Theorem, though that usually represents to a higher dimensional version of this theorem. This is a one-dimensional version, which is, of course, simpler. Lecture 10B is the linear algebra portion. We will review cross products and equations of planes from Lecture 9B, and we'll look at a 5x2 linear system with 5 equations and 2 unknowns, more equations than unknowns, that arises from something called the least squares problem. And we'll talk about the associated linear transformation, and we'll also think about norms like we did in Lecture 9B. So we'll start with bifurcation example 1 here in Lecture 10A. This is the same example as at the end of Lecture 9A, but let's go over it again in more depth. We're considering, once again, the one-parameter family of autonomous ODEs. dy dt equals f sub mu of y equals y squared plus mu. First off, realize this is a first-order ordinary differential equation. Our highest derivative is a first derivative, and this is an ordinary derivative, not a partial derivative. It's autonomous because the right-hand side depends on just y with no t's. But then you might say, well, hey, it depends on this symbol mu as well, and yes, it does. But we're thinking of mu differently than t and y. T is the independent variable, y is the dependent variable. Mu is a parameter. Now, the word parameter has a lot of different meanings, and in fact, when we talk about parametric curves in this context, we think of those as being functions of the parameter t for time. But here we're thinking of it as being something different. Mu is initially thought of as being a constant, but then you say, hey, mu could be anything. So in a sense, I can let the constant vary, as strange as that sounds. And what's most interesting about this stuff is to understand what happens as mu varies. We're really thinking about infinitely many differential equations all at once, infinitely many different phase lines, and we want to understand, are there big changes that occur in the phase line as mu changes? Those are called bifurcations. Okay? So again, mu is the parameter of this infinite family of ordinary differential equations. We want to draw the phase line for various values of the parameter mu. Okay, so like I said at the end of Lecture 9A, to think about this, the most important thing to do initially is to draw the graph of the right-hand side function. But hey, how do you do that when you don't know what mu is? Well, you can pick different values for mu and see how the graph changes as mu changes. So we can graph f sub mu of y versus y for different values of mu. Y is horizontal in this picture, but in the phase lines we want to make y vertical. When mu is positive, you're going to get y squared plus a positive number. That's going to be a graph that looks like this. That's when mu is positive. When mu is 0, you get y squared plus 0. That's this case. And when mu is negative, for example, maybe negative 3, you'd have y squared really minus 3. That would be a graph that looks like this. And it's only in the case where mu is less than or equal to 0 where you have equilibrium points, because the equilibrium points, as we've seen, correspond to the intercepts of the y-axis in this picture. Just one intercept there when mu equals 0, at y equals 0, and 2 intercepts when mu is negative, here and here, those 2 different values of y. On the phase lines, where again y is going to be vertical, we want to draw those points as equilibrium points. They correspond to equilibrium solutions of the differential equations, which are constant functions in the slope field that are the true solutions. But by collapsing all the information into the phase lines, it keeps things simpler. So here's our initial picture. I picked mu to be negative 4 here. This time I'm going to let mu increase as we move to the right. So when mu is negative 4, which is negative, you see you have 2 equilibrium points at plus or minus 2. Let's go back to this picture again. This is going to be now when mu is negative 4, The intercept down here is -4, but the only important thing about that is that it's negative. The right-hand side here is y squared minus 4 in this situation. The horizontal intercepts are where y squared minus 4 equals 0, y squared equals 4, y equals plus or minus 2. This is 2, this is -2, right over here. Those correspond to these equilibrium points. This point becomes this point here, this point becomes this point down there. That's the phase line. Those points stay stationary as time goes by. We call them equilibrium points. They correspond to horizontal solutions of the differential equation. We always want to remember to relate this to the differential equation. Equilibrium solutions. When y is bigger than 2, over there in this picture, f sub mu of y is positive. This graph is above the axis. That means for the differential equation and its solutions, dy dt is positive. Solutions are increasing. Therefore, we put an upward pointing arrow when y is above 2. On the other hand, when y is between -2 and 2, f of y is negative, meaning dy dt along solution curves is negative, meaning solution curves are decreasing. So we put a downward pointing arrow. And finally, when y is less than -2, corresponds to right there, f of y is positive, dy dt for solutions is therefore positive, solutions are therefore increasing, and we put an upward pointing arrow. This equilibrium point is a sink because the arrows nearby are pointing toward it. This one's called a source because the arrows nearby are pointing away from it. You can also have nodes, for example, a point where above it arrows point upward and below it arrows point upward, or vice versa. Those are called nodes. All right, and that actually happens in the next example when mu equals 0. That's when f of y just touched the y-axis at y equals 0. And the function, the right-hand side function, was positive on either side of y equals 0. And therefore solutions, except for the equilibrium solution at y equals 0, are always increasing. So you put upward pointing arrows on both sides. We call that a node. When mu is positive, for example, like +4, then the graph is completely above the y-axis over here. Dy dt is always positive, never 0. Solutions are always going up. Doesn't mean they're always going up at the same rate. Solutions still are going to be sometimes concave up and sometimes concave down, perhaps. Or, well, that could happen in theory. It doesn't happen in this example. Actually, it looks more like this for this example. Sometimes concave down, sometimes concave up, like that. When the graph of f of y is above the axis, it's still going to have a minimum value at y equals 0. Solutions are going to have a minimum slope when y is 0. You're going to get a picture like that for solution curves. Okay? What's linearization? Linearization, coming back to the green curve here, looks at the slope of f at the equilibrium points. Negative there, positive there. So the function changes from positive to negative here, and that's why you have a sink in the phase line, and the function changes from negative to positive right there. That's why you have a source. We can look at the derivative, and whether it's positive or negative, add an equilibrium point to help us decide what the equilibrium point is. What's the bifurcation value where the big change occurs from 2 equilibria to 1 equilibrium point when mu is 1 value, 0, to no equilibrium points? That is at mu equals 0. Sometimes it's denoted by mu star. The star just says that's a special number. The star is not a number itself. It's just saying this is mu star. It's the star of the show. It's a special number. It's 0 in this case. However, we can do even more. We could stitch together infinitely many phase lines. We picked mu as -4, 0, and 4, but what if we did mu is 1.7, or mu is 2.9, or mu is pi? Imagine putting a bunch of phase lines together, infinitely many, and you get something called the bifurcation diagram. To help draw the bifurcation diagram better in general, you want to find something called the curve of equilibria, the curve of equilibrium points, found by setting the right-hand side function equal to 0, and in this case we can solve for y as 2 functions of mu. Subtract mu from both sides of this equation, take the plus or minus square root, you'd have y squared equals negative mu squared equals negative mu. Take the plus or minus square root to get both solutions. These are two functions of mu that I could graph in a new plane, a mu y plane. Y vertical, because I'm going to draw phase lines vertical, mu horizontal. I'm drawing a bunch of different phase lines for a bunch of different values of mu. And these two functions give us a curve, and here's what it looks like. So the blue curve are your two graphs of y equals plus or minus square root of mu. Equivalently, it's the graph of this quadratic equation and this one, where I don't necessarily have to take the plus or minus square root. That is the curve of equilibria, the curve of equilibrium points. For any given value of mu, I pick -4, -3, -2, etc. For example, -3, right there. For that value of mu, the second coordinates of this point and this point are the equilibrium points. That would be square root of 3, plus or minus square root of 3, about plus or minus 1.7. And this is the phase line. You've got arrows pointing upward here, downward here, upward here. This is a sink, this is a source. Interesting, and it should make sense. When mu is less than 0, you always have two equilibrium points that are, this one down here is a sink, this one up here is a source, because the graph is still crossing the axis with a negative slope there and a positive slope there, the graph of f. And they're getting closer together because as mu increases, this graph moves upward and these points get closer together. And they merge at one instant, so to speak, for mu, at mu equals 0, the bifurcation value, also called bifurcation point, where you just have the node. And then they annihilate each other. Once mu is positive, now you have no more equilibrium points. This is an example of a bifurcation diagram. If you Google bifurcation diagrams, you might see some graphs like this. You might see things that are a lot more complicated, actually. Those more complicated bifurcation diagrams, much more complicated, come up in the situation of actually discrete dynamical systems where you are iterating a function as we've done before. Difference equations can get more complicated than differential equations. All right, what is this linearization theorem? Again, also called the Hartman-Grobman Theorem, though again, that's a higher dimensional theorem in general. We're looking at it in one dimension. Theorems can be kind of complicated. We have some hypotheses, some premises, some assumptions we're making in the theorem. Suppose y0 is an equilibrium point. Very important that y0 is representing an equilibrium point. If it's not an equilibrium point, don't try to use the theorem. It doesn't make any sense in that case. Of an autonomous first-order ordinary differential equation, our typical kind right here. Let's erase this top thing here. Actually, let me make another line just closer here. dy dt equals f of y. Okay, so y0 is a number that's going to correspond to a constant function, y equals y0, that's a solution of the autonomous differential equation. That's an equilibrium solution. This is an equilibrium point on a phase line. Where f is called continuously differentiable. What does that mean? You've probably never heard of that phrase before. You've probably heard of continuous and you've heard of differentiable. What's continuously differentiable? It's the official name for a function that's differentiable with an everywhere continuous derivative. So f prime exists and f prime is continuous everywhere on some open interval near y0. I'm going to show you some pretty wild examples where this fails here in a minute. So that's worth keeping track of. You want to not only the derivative to exist, but be a nice continuous function. There are 3 bullet points here. The first one says, if f prime of y0 is negative, then y0 is a sink. The second one says, if f prime of y0 is positive, then y0 is a source. And the third bullet point is there just for completion's sake, but it doesn't really tell you much. If f prime of y0 is 0, then you can't really say much. You need more information to say whether y0 is a sink, a source, or a node. You really need the graph of f. And make sure you graph it correctly. I'm not going to prove this theorem. That's beyond the scope of this course, but we can certainly give an intuitive or visual justification. In fact, I've already done it essentially. When you're graphing the right-hand side function as a function of y, when the graph crosses the horizontal axis with a negative slope, so the tangent line has a negative slope. That means the function f of y is changing in sign at that equilibrium point, where it's 0, from positive to negative. So in the slope field or in the phase line, when y is less than y0, solutions increase, because f is positive. And y is just above y0, solutions decreasing, because f is negative. So they're moving toward the equilibrium point. It's got to be a sink. On the other hand, when you've got a positive slope, I drew these graphs with a little bit of concavity, but that doesn't matter. Tangent line has a positive slope at an equilibrium point, y0, where the function is 0. The function will therefore have to change sign from negative to positive as you pass through y0. In the phase line at the equilibrium point y0, when y is less than y0, this is negative, dy dt is negative, solutions decrease. And when you're just above y0, f of y is positive, so dy dt is positive, so solutions increase. The arrows point away from the equilibrium point. It's got to be a source. What could happen in the situation where f prime of y0 equals 0? There's essentially 4 things that could happen. The graph could look like this at y0. So it doesn't cross the axis. You can see the derivative there is 0. The tangent line is the slope of 0 there. And it doesn't change sign. In fact, it's always positive on either side. In this case, you're going to have a node with upward pointing arrows both above and below it. You could also have the graph of f be below the y-axis. That's going to be a node as well with downward pointing arrows. A couple more things that could happen is you could have it cross the axis but with 0 slope, kind of like the graph of y cubed at y0. So there you actually are changing sign from negative to positive. It is analogous to this situation. It's going to be a source at y0 in the phase line, but the linearization theorem doesn't guarantee that. And the final situation is like negative y cubed, like this. Okay? That's basically what can happen near equilibrium points. There are some wild examples out there, though, that you should be aware of, just for the sake, mostly, of realizing there are wild examples out there. So that means you need to be careful when you're doing theoretical math. You know, you want to apply it to some real-life situation, some real-life model, but whenever you use theorems, hypotheses are important for the conclusion to be valid. So, and you might imagine, well, is there a function whose derivative exists but it's not continuous? Are there some functions like that that are differentiable but not continuously differentiable? In this case, I'm telling you there are. Now, the first one is actually not an example of that, but it's sort of leading up to some other examples. Wild example number 1, dy dt equals f of y equals sine of 1 over y when y is not 0, and 0 when y is 0. Maybe you've seen this function before in your Calc 1 or Calc 2 class. You might want to graph it on your calculator before I show you the graph. It's a very wild function. As y approaches 0, 1 over y is approaching plus or minus infinity, depending on whether y is positive or negative. It's going through many cycles of the sine function, essentially. It's oscillating infinitely often on any little tiny neighborhood of 0. Here's what the graph looks like in red. The red graph is the graph of f. It's oscillating infinitely often with essentially constant amplitude, you might say, even though it's not a periodic function. It makes sense. Sine always has to be between negative 1 and 1. And because this oscillation is infinitely often near 0 and doesn't decrease in amplitude, the limit as y goes to 0 of the red function doesn't exist. This function is not even continuous at y equals 0. And if it's not continuous, it can't be differentiable either. So this example does not satisfy the hypotheses of the linearization theorem. What's the nature of the equilibrium point at y equals 0? Boy, that seems like it's kind of hard to describe. The phase line, to tell you the truth, is going to have equilibrium points that are, well, there's going to be infinitely many of them, and they're going to sort of accumulate on each other. They're going to get denser and denser as you approach 0. You're going to have infinitely many of them. And 0 will be an equilibrium point because I made this function equal to 0 when y is 0. It's a piecewise function. But is it a sink or a source? It's not really either. And you wouldn't really call it a node in the sense we've talked about so far either. The equilibrium points are all massing together almost. Those other equilibrium points besides 0 you could use linearization for and decide whether they are sinks or sources, or just look at the graph if we zoomed in. While example number 2 is very similar, except we put a y in front of the sign of y, sine of 1 over y. We still get infinitely many oscillations near 0, but they're decaying in amplitude because y is going to 0 and we have a y in front of us. The graph looks like this. By the way, the blue graph, I forgot to mention, you can see it is the derivative of f. Here, f, the red graph, is not continuous at y equals 0. Therefore, it's also not differentiable. The blue graph exists as the derivative of the red graph, except when y is 0. It's got a, it doesn't really have a vertical asymptote in the usual sense at y equals 0, but it becomes unbounded. These oscillations for the blue graph get bigger and bigger. That still happens, actually, with this example, though it's less obvious why that should happen. The blue graph's oscillations still get bigger and bigger, unbounded, in a sense, a wild kind of vertical asymptote. But the red graph does decrease in amplitude. It decreases in amplitude so that you could actually apply something called the squeeze theorem to say that this f is continuous, but it turns out not differentiable at y equals 0. The red graph. In both of these cases, I'm talking about the red graph when I say these things. The last wild example tries to tame this even more and has some success. Put a y squared instead of a y in front of the sign of 1 over y. We once again get to decay to 0. The derivative in this case, the blue graph, is not unbounded. It's bounded between approximately something that's slightly less than -1, slightly something bigger than 1. And it's, in fact, even continuous everywhere. It exists everywhere, but it's not continuous everywhere. The derivative always exists, even at x equals 0, it turns out here. But it's not continuous because the limit of the blue graph as y goes to 0 does not exist. So again, once again, talking about f here, f is continuous and differentiable, but not continuously differentiable. The derivative exists everywhere, but the derivative is not a continuous function. That blue graph is not continuous at y equals 0. Sorry, this is hard to see. It says f is continuous and differentiable, but not continuously differentiable. This is supposed to be a period here, but I got it messed up. So just be aware of wild examples for your own benefit of realizing, hey, I should be careful with theorems. Bifurcation example 2 still has a quadratic right-hand side, but I made it more complicated now. Instead of y squared plus mu or y squared minus mu or negative y squared plus mu, I added this extra 4y in it. Let's find the bifurcation value, also called the bifurcation point of mu, for this family. Family because there's infinitely many functions of this type as mu changes. That's why it's called a family. How do you do that? Well, you could try to draw the bifurcation diagram straight away by drawing the curve of equilibrium points. Set this equal to 0 and solve for y as a function of mu. And I will do that. But we don't actually have to make the graph to figure out the bifurcation value. We can just do the algebra. Set this equal to 0. Use the quadratic formula to determine the curve of equilibria, and based on what that curve looks like, maybe even we can tell just from the formulas, we might be able to figure out the bifurcation value. So we're setting negative y squared plus 4y plus mu equal to 0, solving for y in terms of mu. I could multiply everything by -1, so that this is positive y squared minus 4y minus mu equals 0, but I also can just use the quadratic formula straight away. Again, I'm setting this equal to 0. It doesn't equal 0 for all y. Setting it equal to 0 and solving for how y depends on mu in that situation. Quadratic formula, negative b is -4, plus or minus the square root of b squared, 4 squared is 16, minus 4 times a times c, 4 times -1 times mu is plus 4 mu. All over 2 times a is all over 2 times -1. The a here and the quadratic formula is -1, the b is positive 4, the c is mu. -4 divided by -2 is positive 2. The plus or minus really doesn't affect, I don't have to put a -2 down here, I could, but because I got a plus or minus there, I don't have to. Let me do this as well. I factored out a 4 of the thing under the square root, and then I separated those two square roots. These two things cancel here and here. We are taking the plus square root of 4 there, 2, not -2. The negative's taken care of with the plus or minus. So the equilibrium points for a given value of mu are 2 of them in general, 2 plus or minus square root of 4 plus mu. But we are only dealing with real numbers so far in this class. There will be imaginary and complex numbers later. We want this to be a real quantity here. We require 4 plus mu, this thing under the square root there, to be greater than or equal to 0 for this to be a real value, or two real values, which is equivalent to mu being greater than or equal to -4. So evidently what that must mean is mu equals -4 is the bifurcation point, or again, bifurcation value. I'll say both things, I mean the same thing. It's a value, a number for mu where the big change occurs. In this case, I guess when mu is less than -4, like -5 or something, then we have imaginary complex number equilibrium points. Well, no, we don't have any real ones. We're not thinking about complex numbers at the moment. When mu is equal to -4, you just have 2 plus or minus 0, just 2, one equilibrium point. And when mu is bigger than -4, then we have 2 equilibrium points at these two values. And now I could graph this as a function of mu. I'll do that by hand. I'm going to show you Mathematica here in a minute. But you should work at, to some degree, being able to do these things by hand. Remember, for the bifurcation diagram, mu is the horizontal axis, and y is vertical. Here's the bifurcation value, mu equals -4. To draw this diagram, I need to essentially draw the graphs of these two functions of mu. 2 plus or minus square root of 4 plus mu. 2 plus square root of 4 plus mu is going to be a graph that's a horizontal and vertical translation of the square root function. Vertically translated upward by 2 and horizontally translated to the left by -4. This is plus 2 here. The graph of that is going to look like this. And when mu is, if I take the minus square root, it just essentially reflects it across the line at y equals -2. And we'll go through the origin here actually, because when mu is 0, we're going to get a square root of 4, which is 2. 2 minus 2 is 0. It will actually go through the origin in this case. I drew it a different color. I didn't have to. Over here, your phase line is going to have downward pointing arrows. The graph of this function, when mu is less than -4, it's going to look like this. You can check. It doesn't have its maximum on the vertical axis. Sorry, that's off there. It's got its maximum about there. But it doesn't touch the y-axis. It's always negative. We're going to have downward pointing arrows. Solutions for the differential equations are decreasing. At the y equals -4, the bifurcation value, That's where this point's going to be a node, but now with downward pointing arrows. At other values of mu, for mu bigger than 4, we've got two equilibrium points that get further and further apart as mu continues to increase. And we're going to be consistent with these other downward pointing arrows, so we're going to get this kind of thing. Downward pointing arrows, except in between we'll have upward pointing arrows. Is it possible to use the linearization theorem without even thinking about graphs? Yeah, it's a little tricky. Remember, we use the linearization at equilibrium points, so essentially at these points. I plug those values for any fixed mu into the derivative of f mu prime of y, and see if I get a positive or negative number. It's 2y plus 4. If I plug in, for example, I'll just do one of them, 2 plus square root of 4 plus y into that, I'm going to get negative 2 times this thing in the parentheses there, 2 plus square root of 4 plus y. Then don't forget about the plus 4 out there. Distribute this negative 2 through the parentheses here, you'll get a negative 4. Negative 4 plus 4 is 0. This simplifies to minus 2 square root of 4 plus mu, I meant, sorry. This should be a mu here. Mu right there, mu right there. I'll go ahead and put the mu in right here. So as long as mu is bigger than negative 4, this is going to be a negative number. This is negative when mu is bigger than negative 4. It equals 0 when mu is negative 4. When mu is bigger than negative 4, it's negative. So you're going to get a sink at the bigger equilibrium point, which you can see. Those are sinks. These points right here. So we can't use the linearization theorem purely symbolically. This, by the way, is an arrow here. This thing is less than 0 when mu is greater than negative 4. Our next example is even harder. I do need to do the Mathematica here. I'll do the Mathematica at the end of these examples. It's a cubic right-hand side function. For my students, this happens to be the same as one of the examples in the textbook by Blanchard, Devaney, and Hall. How in the world should we do this? We want to once again find approximate bifurcation values. This time, there actually is going to be more than one of mu for this family. And draw the bifurcation diagram. I said to do it by hand here, and you can do it by hand, but it is trickier. I think as far as finding the approximate values, well, I guess we probably could do it here, I think. Let's go ahead and do it, try it by hand. See how far we can get. So again, mu is horizontal, y is vertical. To find the bifurcation curve with the quadratic examples, I solve for y as a function of mu. To solve for the, I meant to say equilibrium curve of equilibria. To solve for the curve of equilibria in this situation, it's actually better to solve for mu as a function of y. Take this thing, set it equal to 0, and solve for mu in terms of y. I get to subtract y cubed from both sides after setting equal to 0, add 2y squared, and subtract y. What is this function? Is it f? No, it's not f. I'd have to give this function a name, perhaps. G of y. That's a cubic function of y. And if I were to graph it in this plane, I'd actually want to graph it sideways. Or if you happen to have a mirror, well, let's see. If you happen to have a mirror, and you hold the mirror like this and you turn your head sideways like that and look in the mirror, then it will look like the y-axis points to the right instead of upward, and the mu-axis points upward instead of to the right. Get a mirror, turn your head sideways, turn the mirror like this, look at it, the object in the mirror. Then it'll look like an ordinary graph. But I don't want to actually deal with mirrors. I want to just draw the graph the way it is. It's a cubic function of y. It's, in fact, I could figure out its intercepts. Let's factor out a negative y, giving me y squared minus 2y plus 1 if I factor out a negative y. And this is kind of nice. This is negative y times 1 minus y quantity squared. It's got y-intercepts that are vertical at 0 and 1. And the one at 1 right there is going to be a double root. This is 1 right here. Cubic, getting bigger, or excuse me, going to minus infinity as y goes to plus infinity. So the graph's got to look like this over here. Goes to, y goes to, mu goes to minus infinity as y goes to plus infinity because of the negative sign there. Wish I hadn't put the 1 there. This 1 right there. Okay. And going to plus infinity as, let's see, as mu goes to plus infinity as y goes to minus infinity. And there's a double root at 1. It's got to look like this, actually. If you turn your head, look in the mirror sideways, it'll look correct. Okay, that's 1 right there is the value of y right there. To find the bifurcation values, evidently one of them is at mu equals 0. And the other one is somewhere right there. In fact, with the graph sideways, it's a local minimum value of this g function. So let's differentiate the g function. Fun, fun, fun. G prime of y, g prime of y is negative 3y squared plus 4y minus 1. Set that equal to 0, solve for y. To find the critical points, one is going to be at y equals 1, actually. The other one is going to be some value of y between 0 and 1. Actually, it's not too hard to use the quadratic formula here. Sorry this is kind of going long, but it's pretty important. If I set this equal to 0 and solve for y, with the quadratic formula, I'll get negative 4 plus or minus square root of 16 minus 4 times 3 is 12, over 2 times a is 2 times negative 3. That simplifies to positive 2/3, right? 4 cancels with the 2, the minus signs cancel. Minus plus or minus, it doesn't matter. That's the square root of 4 there, which is 2. Cancel the 2's, looks like plus or minus 1/3. So roots are 1 and 0, and 1/3, excuse me. 1 and 1/3. This is a 1/3 right here. And plug that back into the g function to find the minimum value of mu that's going to be a bifurcation value. G of 1/3, looking at this formula right here, is negative 1/3 cubed, negative 1/27. Cube first, then do the minus sign, plus 2 times 1/3 squared will be 2/9 minus 1/3. Sorry. So that'll be negative 1 plus 6 minus 9 over 27. That's going to be negative 4/27. That's negative 4/27 there. Now to finish with the bifurcation diagram, I want to draw phase lines too, including in between the bifurcation values. There's 2 bifurcation values. There's also mu star equals 0 as well. And you'd want to think about the graph of the original f function to figure out what direction the arrows go, not the g function. graph of f. In this case, it's a cubic, but now the cubic is going to look more like that, going upward as y goes to infinity. Yeah, it's got to be going upward here and here. It's going to have a node with upward pointing arrows here and here. Excuse me, no, I'm sorry, it's going to be downward pointing arrow. I'm sorry, I'm getting confused. It's a mess. Okay, this should be downward pointing. This should be downward pointing. Upward pointing, upward pointing. Upward, downward, downward. These are all downward pointing here. Upward, downward, downward. Upward and downward here and here. So this equilibrium point here, for any given value mu less than negative 4/27 is a source. This one over here, when mu is bigger than 0, is a source. Here on this one, mu equals 0, we've got a source there and a node there. Here when mu is negative 4/27, we've got a source here and a node here. And when mu is between negative 4/27 and 0, here, here, and here, we've got 3 equilibrium points. This one's a source, this one's a sink, this one's a source. Sorry, it's difficult to see and pay attention to. It's not an easy thing, it's very tricky. I think for the sake of time, I'm not going to do this logistic model with harvesting because I wanted to show you some Mathematica code. We'll come back to this for lecture 11A. Let me just mention at the moment, the harvesting part of it is the minus h part. I mentioned this, I think, a couple lectures ago, maybe lecture 8A. Harvesting is like fishing. It's a constant, so it's like we're fishing at a constant rate. And we're wondering, what does this model tell you based on different values of h? And are there any bifurcation values of h? And what are the real-life implications of h changing, like allowing more fishing to the fish population? Okay, we'll look at that in lecture 11A. Let's end lecture 10A by looking at Mathematica. Think more about examples 1, 2, and 3 here. And again, I have to go through the code fast here for anybody who happens to be watching. My students, like I've told them, they'll get more practice with this. I put the clear f in here just to be safe. But here I'm defining the f function for this first example, y squared plus mu. Notice again, the mu is in a subscript here, but I do need an underscore because Mathematica doesn't know it's a parameter. It thinks it's a variable. Plot the function, y going from negative 4 to 4, the right-hand side function. All this other stuff is just to make it look nice. Manipulate makes an animation. Here's the n square bracket for the plot, and here's the n square bracket for the manipulate. After the plot, this part, first of all, this part right here lets mu go from negative 4 to 4. The appearance just allows us to see the value of mu, and the label style large just means it's bigger than the default. So this is the graph of the right-hand side function. As mu increases, I probably should have put dots at the interception, y-intercept points there, but I didn't. As mu increases, the graph gets translated upward. So for the phase line, as mu increases, we go from having 2 equilibria, like right now, to 1 right when mu is 0, to none when mu is positive. You can see the value of mu right there. I did make the slope field as well. It's always good to remember there really is a slope field in the background. See, it changes, mu changes. We see, instead of equilibrium points merging and annihilating, we see equilibrium solutions emerging and annihilating each other. You can see when mu is bigger than 4, bigger than 0, you have this kind of graph that's concave down at first, then concave up for solutions. And I can make the phase line for various mu's. I guess I did that and combined it with the other graph, and here I made dots. So these dots do represent the equilibrium points in the phase line. They have the same y coordinates. You can think about how the errors change as mu changes as well. I did enter code here to make a bifurcation diagram too, the one you saw in the PowerPoint. Example 2, let's just look at the f function for these last two examples, then we'll be done. Now the f function looks like that, and as mu increases, we go from having no y-intercepts to 1 when mu is -4, to 2 when mu is bigger than -4. The bifurcation value was -4. And for the cubic, once again, since we're adding mu really represents a vertical translation. The cubic, this is f, gets translated upward as mu changes. We go from having just one equilibrium point right there for the phase line, when mu is less than -4/27. When mu equals -4/27, right about here or so, we get an equilibrium point is born. Right there would be a node. The equilibrium point right there, because of linearization, the derivative is positive, it's going to be a source. When mu is between -4/27 and 0, for example, like right here or so, we've got three equilibrium points for y, here, here, and here. This one has a positive slope, so it's a source. This one has a negative slope, so it's a sink. This one has a positive slope, so it's a source. And when mu is bigger than 0, we're back to just one equilibrium point right there. What about the bifurcation diagram? Contour plot will make it, it essentially plots f mu of y equals 0 here. There's the bifurcation diagram without the phase lines drawn. I didn't want to bother drawing the phase lines in Mathematica. And here actually is a system of equations you can solve to figure out not only the bifurcation values of mu, but the value of y at those corresponding equilibrium points. I'm solving where f of y is 0 and where f prime of y is 0. You might want to think about why that's a good idea. Solving for both mu and y. When mu is -4/27, that's a bifurcation value, and the one equilibrium point is born at y equals 1/3. Yeah, that corresponds to that point right there in the y direction. It's 1/3. And when mu is 0 and y is 1, that equilibrium point, these two equilibrium points merge and annihilate each other. So another bifurcation occurs when mu is 0. The equilibrium point up there when mu is 0 equals 1. Okay? So I know that's quite a lot of information to try to take in. We will do more examples in lecture 11a.